Well,
good morning, everyone, and thank you for joining us today. Today's presentation is brought to you by the Transportation Learning Network. TLN is a program of the Upper Great Plains Transportation Institute at North Dakota State University and is a partnership with the 4 state DOTs of North Dakota, South Dakota, Montana, and Wyoming, and the Mountain Plains Consortium, which includes 8 universities in Colorado, North Dakota, South Dakota, Utah, and Wyoming. A little bit about the MPC. The Mountain Plains Consortium theme is transportation, infrastructure, and operations to support sustainable energy development and the safe movement of people and goods. MPC is a competitively selected university transportation center sponsored by the U.S. Department of Transportation through its Research and Innovative Technology Administration. Our speakers today, we have Dr. Abbas Rashidi. He's an assistant professor in the Department of Civil and Environmental Engineering at the University of Utah. His research focuses on developing image, audio, and signal processing techniques for various applications within the civil infrastructure system. He is the associate editor of ASCE Journal of Performance of Constructed Facilities and assistant specialty editor of ASCE Journal of Construction Engineering and Management. His research has been funded by the U.S. DOT, UDOT, so Utah DOT, the CPWR, and NSF, which results in over 50 published papers in journals and conferences. Additionally, we have Chandler Cross joining us today. He's a structural engineer. He has recently received his master's degree in infrastructure engineering from the Department of Civil and Environmental Engineering at University of Utah. He also has a BS degree in civil engineering from Georgia Southern University. He's an expert in using advanced technologies for asset management and inspection purposes. With that, Chandler and Dr. Abbas, I will turn the presentation over to you.
So thank you, Chris, for the introduction, and good morning, ladies and gentlemen. So I just give a quick kind of overview about the entire project, and then I will pass it to Chandler, and Chandler will provide technical details about this project. So basically, as you know, nowadays, asset management is a critical task for all DOTs, state DOTs, and there are several technologies used for this purpose. So mainly LiDAR or laser scanning based technologies is the current common practice for handling the job. So the point is that with advancement in digital technologies and computer vision algorithms, now photogrammetry is also another emerging technology for 3D reconstruction of various scenes and objects. So for this project, we try to basically do an evaluation and comparison between photogrammetric technologies as well as LiDAR technology for asset management for, in particular, Utah Department of Transportation. So with this just very brief introduction, I pass it to Chandler to just provide some more technical information. Please feel free to stop us, ask questions either during the presentation or after the presentation. Again, thank you for your time.
awesome. Well, thanks everybody for joining us today. As Abbas said, my name is Chandler Cross, and I was the project lead over the duration of this project. So we'll go ahead and get started and tell you about give you a little presentation on our research and image-based 3D reconstruction of our Utah roadway assets. So first, we have a bit of an outline for you guys. So why was this project necessary? Some data acquisition technologies we used, LiDAR and photogrammetry. We'll go through a little bit of the software testing that we did throughout the duration of this project. Our different data collections, whether it's like mobile highway asset management, UAS highway asset management, pedestrian access ramp inspections, and then we also did some supplementary case studies of pavement distress and bridge inspections. We'll talk about some data evaluations for the case studies mentioned above. So what did we get out of the data that we collected? Some limitations and challenges that we ran into, some recommendations for carrying on with this type of research and technologies, a bit of a cost-time analysis between the technologies, a summary, conclusion, and then our acknowledgements. So why was this project necessary? Utah's transportation system is one of its most valuable assets, and it's valued at more than $45 billion. And there's various tiers of assets within UDOT, and these are based on their value and their financial impact. So items such as pavement and bridges, ATMS and signal devices are going to be tier 1 assets, and that's because there's the most money invested in them and there's the most money to be lost if they are poorly managed. The tier 2 assets are the main focus of this research, though, items such as mostly focused on signs and ADA ramps. Asset management is of utmost importance to ensure an efficient and safe transportation system, and these asset managers must have access to up-to-date information regarding all of the assets and their conditions, which requires a fast, efficient, and affordable data collection procedure. It was necessary to test whether photogrammetry can be considered as an acceptable alternative to LiDAR within UDOT because, as Abbas mentioned, LiDAR is the traditional data collection procedure for many of these case studies, and we wanted to see whether photogrammetry can be considered an acceptable alternative. So some of the data acquisition technologies that we used for LiDAR. On the left here, you see a VX15 laser scanner mounted to the bottom of a big drone that we use for our UAS, Highway Asset Management. We also used a terrestrial LiDAR scanner, which was a Maptec iSight 8820. It's a long-range mining scanner, but can also be used for close-range scans. And then for the mobile LiDAR for Highway Asset Management, we obtained models from UDOT, and these models were provided to them through Manley Communications, who is an outside company that UDOT currently sources their asset management and data gathering to. For photogrammetry on this left side here, you see a GoPro Hero 8 Plus mounted to the front of the vehicle, and this is what we used for our mobile highway asset management. We have a Fujifilm X-T30, which is just it's a mirrorless camera with a 28 megapixel sensor, so it gathers a lot of data, and we use that for the pedestrian access ramps. And we also used a DJI Mavic 2 Pro drone for photogrammetry. So talk a little bit about the case studies that we did for asset management. The main case studies were the highway asset management. Like I mentioned, we use mobile LiDAR, so we obtained those models from Manley Communications. We used mobile photogrammetry, where we had the GoPro attached to the front of the vehicle. And we also used UAS LiDAR and photogrammetry with those 2 drones that I showed you. And we created highway models and evaluated them using each one of these methods, and we'll get into each one a little bit later throughout the slides. We also did our pedestrian access ramp inspections using terrestrial LiDAR, that LiDAR scanner that you saw me using in the previous slides, and using photogrammetry, that Fujifilm X-T30 camera. And as I mentioned earlier, we also did some supplemental case studies. So we have our pavement distress analysis, which again, we used the terrestrial LiDAR scanner and mobile photogrammetry, the GoPro Hero 8 mounted to the front of the vehicle. And we also did bridge inspections and compared mobile LiDAR, terrestrial LiDAR, and our mobile photogrammetry. So one of the first things that we had to kind of decide was which software we were going to use. So we had to go through a little bit of software testing. Now there's a number of softwares on the market, and we needed to decide which one was going to provide the best overall point clouds for all of our case studies. And we tested both of our data collection procedures. Now let me explain a little bit what I mean by traditional and linear. So in this image you see here on the bottom left, this would be considered our traditional data collection procedure. For photogrammetry, usually images are captured in a circular pattern around the object of interest. For reconstruction, that way that there's plenty of overlap within the images. This is the capture pattern that most of these softwares recognize. But we also had to use linear data collection procedures. And what I mean by that is when we're collecting data on a highway or a roadway, these roads are linear by nature. So as we're driving down the road, the camera's staying in one spot and gathering images from the same line of sight, essentially, just getting farther down the road. So we needed to see which software could handle traditional data collection procedures for like our pedestrian access ramp, and also linear data collection procedures for our roadway asset management. So what we did was we uploaded the same data into each software for comparison. So we did this building down here and compared them. We gathered put the same data of this building into all of these softwares, and then we took 163 images from a city street data collection, which is a linear data collection, and put them into these softwares and evaluated which ones provided us with the best output using both procedures. So we have a bit of a comparison table here for you. So the number of images registered out of 163 images, the processing time, the number of generated points in the point cloud, and the overall point cloud quality. So keep in mind that these point clouds are using the traditional data collection procedure. So we want to see a roadway and its surrounding elements, right? So Agisoft, it's a bit of a mess. There wasn't really a whole lot going on. Couldn't really see a roadway. Reality capture, we're getting closer to a roadway model, but it's still kind of in disarray. There's a lot of big blocky stuff going on. 3DF Zephyr is where we started getting into better models. It looks a little bit fuzzy from the zoomed out view, but as you get closer, you can start to see the pavement lines and the faces of the signs and such. So 3DF Zephyr was one of the better softwares at the start. Context capture, which we ended up using for nearly all of our case studies for both pedestrian access ramp and highway asset management because it provided us with very good models. As you can see from this image, you can tell that it's a roadway. It has its road pavement, it's got its pavement markings. You can't really see the signs that well, but this model was much better than Agisoft Reality Capture 3DF Zephyr, and it was better than our Pix4D model. So after this little bit of analysis, we decided that context capture was probably the best software for us to use for these case studies, and it did end up working out great. So let's talk a little bit about the data collection procedures for our highway asset management. We tested different cameras. So we started with a GoPro Hero 3 Plus, which was, it had limited video resolutions and frame rates, and it also didn't have any in-video stabilization. So after creating a few successful asset management models, we decided that it would be best to upgrade the camera, which is what we did. We then went to the GoPro Hero 8 Plus, which was the newest GoPro at the time. It allowed for far better video resolutions to frame rates, and it also, the most important thing about the GoPro Hero 8 was it had video stabilization inside of the camera. So even if you're driving on a rough section of roadway where there's a lot of bouncing and jostling going on, the video is stabilized and smooth. So when you extract those frames, there's no blurriness within those frames. We also tested a hood-mounted versus a roof-mounted camera. But as you can see from these images down below, this is the roof-mounted GoPro and this is the hood-mounted GoPro. When we had the GoPro mounted on the hood, it was a little bit higher up, so it was a little bit closer to the highway, like the overhead highway signs, but it was hard to position the camera in a way such that the hood of the vehicle was excluded from the frame without including too much sky. So we ended up coming to the conclusion that a hood-mounted GoPro gave us a good field of view. It didn't include the hood of the vehicle or any vehicle components in it, and it also excluded a good bit of the sky. If you have too much blue sky within these frames, the softwares have trouble extracting these features, and it just makes it harder to process and make a good point cloud model. We also tested different fields of view. So you can change the field of view within these cameras. The linear field of view tended to be a little bit too narrow and excluded signs that line the side of the highways. And the super view was a little bit too wide. It was stretched. So whenever we would pass underneath highway signs, those frames just before you pass underneath the highway signs would show warping and bending. So we ended up sticking with the wide field of view because it gave us the perfect field of view. We could see side highway signs, overhead signs, and there was minimal distortion. We also tested different viewing angles. So we tested whether it would be best just to mount the camera pointing straight forward on the vehicle and processing the model that way. And we also tested whether it would be best to mount the camera facing 15 degrees to the right, 15 degrees to the left, and straight, and trying to merge all of those views into one model. But it ended up turning out that a camera mounted straight worked out best for us. And the mobile LiDAR models were obtained through UDOT. As I mentioned earlier, Manly Communication does all of UDOT's asset management data collections and processing. So we were able to obtain those models that Manly had given to UDOT for our comparison purposes. This table is just kind of a brief overview of the six best and most focused on models for this particular case study. So we just recorded things such as lighting conditions on this particular time of day, how long it took to acquire the data, the speed we were traveling, model length, number of registered images compared, aligned to the total, how long it took to process, and the overall number of point cloud points within these point clouds per model. So let's talk a little bit about our UAS asset management, so using drones. UAS stands for Unmanned Aerial Systems, and we use these for comparison for our highway asset management purposes. We use 2 drones with the help of the aviation department within UDOT. We used, on this left side, you can see a DJI M600 drone with this mounted VX15 LiDAR scanner underneath. And that was for LiDAR, and for photogrammetry, we used a DJI Mavic 2 Pro. We flew the drones with UDOT personnel to gather data regarding previously constructed highway models. So we obtained models for a particular section from UDOT that Manley had previously generated. We then recreated that section using our mobile photogrammetry procedures, and then we went out in the field with UDOT personnel to fly drones over this section of highway to recreate. So we have 3 different data collection procedures essentially to compare to each other. The drones were flown 250 feet above the roadway, and it wasn't directly over the roadway. You're not allowed to fly these drones over active traffic. So these drones were actually flying over the medians of the roadway, so it's not actually flying over any active traffic. The LiDAR scanner only emits laser pulses straight down from the scanner. So if you're looking at this image right here in the center, this little glass box is where the LiDAR points come out of. So you can see that it only can shoot out and, out, down, and up from this glass box. It can't really angle outwards. But the Mavic 2 Pro has an adjustable camera angle, and we set that angle 60 degrees below the horizon. And I'll talk a little bit later about why these angles are important. Let's talk about our pedestrian access ramp inspections. So for our pedestrian access ramps, we met with UDOT Ped Ramp experts to discuss the pedestrian access ramp elements and the inspection protocol that UDOT uses whenever they go out to inspect these pedestrian access ramps. So you can kind of see I have this little color-coded map here and what each area is. But UDOT uses a C170 pedestrian access evaluation form to evaluate these pedestrian access ramps. And what they do is they go out into the field with a smart tool, smart level, so it just measures slopes essentially, and a tape measure. And what they do is they have to measure different cross slopes, which is perpendicular to the direction of travel, and running slopes, which is in the direction of travel, for each one of these pedestrian access ramp components. And these measured slopes have to be within these given tolerances from this UDOT C170 evaluation form in order for the pedestrian access ramp to be considered passing. And if a ramp fails, then it needs to be talked about what needs to be done to fix this pedestrian access ramp and make it an acceptable and passing ramp. So the main takeaway from this UDOT meeting and gathering information regarding these ramps is the slope tolerances are very important for UDOT to pay attention to because it can be the difference between a ramp passing or failing inspection. For photogrammetry, we used a Fujifilm X-T30, like I mentioned earlier, and we took about 25 to 30 pictures per ramp. This camera has, I believe it's 26 or 27 megapixel sensor. So each one of these images is gathering a lot of data on these ramps. And for LiDAR, we use the same MapTech iSight 8820 LiDAR scanner. And as I mentioned, it's a long-range scanner, so it's capable of capturing a lot of data, and we only needed one stationary scan per pedestrian access ramp. You can, with this MapTech laser scanner, it comes with a tablet pad, and you can choose your scanning area. So we would just choose the entire area of the ramp, do one scan, and take it back for post-processing. Similar to the highway asset management data collection table, we have something similar for pedestrian access ramps. And in this case, we have our image-based reconstruction and our LiDAR-based reconstruction. And we're comparing things such as in-field data acquisition time, the number of aligned images to the total number of images input into the software, the processing time, the number of points in the point cloud, and the overall file size. And we'll get into these things more as I go through these presentation slides. So let's talk a little bit about our supplemental case studies, our pavement distress and bridge inspections. So for our pavement distress analysis, we compared how accurately mobile photogrammetry could map pavement distress compared to a stationary LiDAR scan. And for the LiDAR scan, we use the same MapTech laser scanner. And for photogrammetry, we use the same GoPro Hero 8 Plus with modified asset management collection procedures. And what I mean by that is rather than having the camera pointed straight and driving at, highway traveling speeds, we were in a secluded roadway where there wasn't much traffic around, so we could drive slow, and we also angled the camera down to face just on the pavement. And then for our bridge inspections, we compared a mobile LiDAR point cloud, a terrestrial LiDAR point cloud, and a mobile photogrammetry point cloud. The mobile photogrammetry point cloud was created using just our traditional asset management collection procedures on the highway. And what we did was we evaluated the width of each diaphragm, so 11 separate locations on this bridge span, to the length of the total span. One thing you'll notice as we get later into the data evaluations was there's no measurement extractions for the photogrammetry model, and that's because the photogrammetry images were unable to capture any data regarding the underside of the bridge, and I'll talk a little bit about that as we get into the data evaluations. So let's talk a little bit about the data evaluation for the highway asset management that we did. So how we evaluated the data that we gathered was a few different ways, and they change per case study. So we calculated the reconstructed sign ratio error, and what that is it's the ratio, the width over the length of the actual sign in the real world to the width over the length of the sign that was generated within the model to see how geometrically accurate we're getting with these reconstructions. We also calculated our sign densities, so the number of points per square inch of each one of these signs. And we have these two measurements, the standard deviation and the coefficient of variation. Now these are referring to our calculated sign density. Our standard deviation is measuring how far each single measurement deviates from the average of the group. And our coefficient of variation is the measure of the variability within our group. And those values will make a little bit more sense as we look at our data evaluations, what we got from comparing the models. So for our photogrammetry averages, we had an average reconstructed sign ratio error of 4.33%, average sign density of 14.6 points per square inch, and a standard deviation 14.6, coefficient of variation of 0.49. Now, our errors are similar between photogrammetry and LiDAR, with 4.33 coming in at photogrammetry and LiDAR having a 3.48. One thing you'll notice, which I'll talk about in the next few slides, is the sign densities. The sign densities for the photogrammetry models were much more dense, and that just goes for the model as a whole. The photogrammetry models were much more dense than the LiDAR models. And I'll talk a little bit to that in the next couple slides as to why we think that is the case. The next important variable to look at here is the coefficient of variation. Now, this is our measure of variability within these sign densities. Now, the lower our coefficient of variation, that means there's less variability within the model or more uniformity. So what this is saying with these values right here is that with a coefficient of variation of 0.42 for LiDAR and 0.49 for photogrammetry, LiDAR had a slightly more uniform distribution of points throughout its point cloud, even though the photogrammetry models were much more dense. So we also evaluated the overall point cloud density of these point clouds for photogrammetry and for LiDAR. And how we did that was using the number of neighbors algorithm in the post-processing software that we were using. What this algorithm does is it imposes circles of a user input radius. We used 1 centimeter all throughout these point cloud models. What the program then does is it counts the number of points within each one of these 1 centimeter radius circles. And the data is output in the form of a histogram, which I have on the next slide for you guys to see. Now, as I mentioned, the photogrammetry point clouds were much more dense than the LiDAR point clouds. And LiDAR tends to produce very dense models. But after many conversations with UDOT personnel who have a lot of contact with Manly, we came to the conclusion that Manly Communications most likely uses smart technologies to limit the amount of data gathered. And what I mean by this is when Manly is gathering data, as soon as they start their systems, they can manually start and stop the data, like start and stop the data gathering. But they have to use, whether it's machine learning or smart algorithms to limit the amount of data gathered, because if these LiDAR scanners that Manly has mounted on their vehicle, if they are gathering data, at 60 miles an hour going down the highway, if they continue to gather data at the same rate of speed that they travel at highway speeds as they would on, a city road where they're traveling 20 or 30 miles an hour, they're going to be gathering a ton of redundant data. So Manly most likely uses smart technologies to limit the amount of data that's gathered based on the speeds that they're going so that they don't have redundant data. So let's look at these histograms using the number of neighbor algorithm that I was mentioning. Now the red areas are the most dense, and then it gets less dense as you move farther away from the sensor. So this red area right here, you can obviously tell is where we were driving. And as the reconstructed scene gets farther from the sensor or the camera, the model becomes less dense. Now let's talk a little bit about these graphs down here. So this is the output that we get from the number of neighbors algorithm. Over here on the y-axis, we have our count. The count is the number of points within that user-defined circle that we talked about. So for the photogrammetry model, let's look at our average point up here. We've got 1.5 times 10 to the 6th, so 1.5 million points. And down here, we've got our number of neighbors, so 160. That means there is 160 circles with 1.5 million points within those circles. For the LiDAR model, if we come over here, we've got about 20 circles with about 35,000 points within it. So for photogrammetry, we're looking at 160 circles with 1.5 million points. And for LiDAR, we're looking at about 20 circles with only 35,000 points. So the photogrammetry models are much, much more dense. Let's talk a little bit about our Uas Asset Management. So LiDAR was unable to capture any signs due to the limited scanner angle. And that goes back to what I was mentioning before. But the photogrammetry could provide accurate sign locations. So we couldn't necessarily see the sign surfaces exactly, but you could tell that there was a reconstructed sign there and their location was accurately preserved. Both technologies accurately map the surrounding terrains, and both, whether using a LiDAR drone or a photogrammetry drone, could possibly be used for bridge structural inspections, but a more thorough data review would be needed for those cases. This is just kind of a close-up of what I was mentioning. So for our LiDAR model on the left, you can tell that this is supposed to be an overhead sign right here, but it's kind of squashed. You can't really tell that there's signs there, and that's due to the scanner angle. But if we look at our photogrammetry model, you can see that we've got our overhead signs mapped in there. We have our roundabout sign in here and even our exit sign back here. So our sign locations were accurately preserved, but since we were flying 250 feet above the roadway, the sign densities the signs weren't dense enough to extract measurements from. So let's talk a little bit about the pedestrian access ramp inspections. We computed errors for how much each model deviated from the in-field measurements. So I went out in the field with UDOT personnel and conducted in-field inspections on 6 pedestrian access ramps. And we did these inspections per their normal protocol. And then we reconstructed these same pedestrian access ramps using LiDAR and using photogrammetry and compared the in-field measurements to the extracted measurements from photogrammetry and LiDAR and measured how much the reconstructed technologies deviated from the measurements that we extracted in the field. We also evaluated the consistency of the results. So the standard deviation and the coefficient of variation for the highway asset management portion, they were measuring and referring to the distribution of points within the point clouds, but our standard deviation and coefficient of variation are measuring the uniformity of our calculated error measurements. So we have just a brief overview of the different ramps, different technologies, and the slope errors for each one of the technologies in each ramps. So the overall error for photogrammetry was 0.32 and LiDAR was 0.19, so very close. Standard deviation for photogrammetry 0.15 and 0.04 for LiDAR. And then the important variable to look at is the coefficient of variation. So for photogrammetry, we have 0.48, and for LiDAR, we have 0.24. So LiDAR was slightly more accurate, and it had more uniformity within its measurements. It had less variability. Let's talk a little bit about pavement distress. So what we did was we found an area of pavement that had quite big pavement distress in it, a big pavement crack. We scanned that area of pavement using one terrestrial LiDAR scan, and we used that LiDAR point cloud as the ground truth model, assuming that it's going to be extremely accurate. So the models were registered using ground control points. And what I mean by that is we used known ground control points in the LiDAR model and in the photogrammetry model and aligned the photogrammetry model to the LiDAR model using those ground control points. The on-site measurements indicated the widths of the target pavement crack are in the range of about 2 to 4 centimeters. So after registering these point clouds and getting them aligned, 99.3% of equivalent point pairs have a distance of less than 0.4 centimeters. So they were very closely aligned. The maximum deviation is 3.25 centimeters, and that's shown by the red areas in this model over here that you see. But the majority of the crack is color-coded with green, which means that the image-based point cloud deviates roughly about 1 centimeter from the ground truth model. And a little bit about bridge inspections. So photogrammetry is unable to capture any data regarding the underside of the bridge, and this is due to the camera's field of view. And what I mean by that is whenever we're driving on these highway sections with our camera mounted to our vehicle, it's pointing forwards. So as we're passing underneath the bridge, the camera is still pointed forward, so it can't really gather much data regarding what is underneath the bridge. If the camera was angled up, it could possibly gather more data, but for the purposes of our asset management collections, we wanted the camera mounted straight. However, the side of the bridge facing the camera as you're driving up to it shows details very well. You can even see connections. So then we have our mobile and terrestrial LiDAR. The terrestrial LiDAR we obtained from UDOT that they had previously done, and the mobile LiDAR, again, we got from UDOT that Manley Communications had completed. So we calculated the percent error of the diaphragm width to the span length of the two different LiDAR methods just to see how closely aligned they were, even though they were using two different LiDAR procedures. One was mobile and one was terrestrial. However, the mobile LiDAR only deviated about 1.29% from the terrestrial LiDAR model, so they were very closely aligned. So let's talk a little bit about some limitations and challenges that we encountered throughout the duration of our research. The largest factor that we found directly affecting point cloud quality is speed. We were unable to create a good model over 50 miles an hour. As you pass 30 miles an hour, your key point matches begin to decrease. And that's what this little graph is showing right here. What we did was we did one section of road at speeds less than 10 miles an hour all the way up to speeds of 50 miles an hour. And we did a key point analysis at different locations of these models to see, at different locations and at different speeds to see what type of key point matching we're getting. Key point matching is essentially the program aligning points in consecutive frames to have a close alignment and reconstruct this point cloud. So the higher number of key points that you have aligned, the more accurate and better your point cloud model is going to be. And after 30 miles per hour, your key points begin to decline, which means it's harder to generate a model, and the models are not as accurate as they are at slower speeds. Poor lighting conditions are also a challenge. So as you can see from these images on the right, good lighting conditions mean that the sign is perfectly illuminated. There's no reflections, no heavy cloud cover or light shining into the center of the camera, because as you can see from the poor lighting condition image, with light shining into this sensor, it really darkens these signs and these pavement markings. So it's imperative to collect data whenever there are good lighting conditions, and that's not always in our control. Vehicular obstructions can also cause problems. That's just the nature of roadway travel. As you're on a highway, if you're collecting data and a car passes you to your left or right, it may block out a sign that you were hoping to gather data on. So you would either have to essentially collect data on that section of roadway again if the sensor wasn't able to gather data on that sign because there was a vehicle in the way. So that's just kind of the nature of data collections on the road. And the photogrammetry point clouds are very large files, but downsampling can help manage these storage problems, which I'm going to talk about in the next slide. So our original photogrammetry point clouds can be very large, some as large as 30 plus gigabytes, and these are for relatively smaller models, less than a mile. So these models can have very large file sizes. So what we did was we wanted to downsample each model, or essentially take away points to see how much quality and accuracy was lost. So what this table is showing you essentially is we have evaluated the number of points at 100% of the points there, what the file size is, and what the visibility of the point cloud is. And then we took away 25% of the points and evaluated, took away half of the points and evaluated, and then we took away, again, 3/4 of the points and evaluated what the point cloud looked like after only having 25% of the original points left. These signs right here kind of show you an idea of the visibility that we're looking at. So great visibility, very dense model, no sparsity really at all. And then on the poor end, you can still see that there is some, you can still read what is on the sign, but you can tell that our density is getting less. The points are getting a little bit more sparse. It's very beneficial to downsample these models. The models, nearly every model, even after downsampling by 75%, retained its data accuracy. These smaller models, for example, if you look at Model 1 at 100% of the points, we're at 11 gigabytes. And after taking away 75% of the points, we're at 2.9 gigabytes. And we still have good visibility within the model. Data accuracy is still retained, and it makes it easier to transfer these files between parties. It also reduces the amount of storage needed in an office, which may help your processing be a little bit smoother. So some recommendations for you. Asset management. It's important to pay close attention to speed. As I mentioned, speed is the largest factor that affected our key point alignment and our point cloud quality. So it's imperative to drive as slow as traffic allows while still being safe. Best to keep it under 50 miles per hour if possible. Choose the optimal time of day for the lighting conditions. So if you're going earlier in the morning when the sun is rising from the west, it's best to drive west or north. And now these may change a little bit depending on the area that you're living in. You're going to have to kind of evaluate where the sun rises and sets and decide what the best directions to drive will be at that given point of the day. Record in a higher number of frames per second, even though you may not use all of the frames for processing. So for our data collections, we used 2.7K resolution at about 120 frames per second for all of our data collections. But for most of our models, we only use around 50 to 90 frames per second. So we just wanted to make sure we had as much data as possible, even if we didn't need to use it all. As I just mentioned, downsampling models can play a huge factor in easing data storage and data transfer between the parties. And also using a powerful processor can help streamline point cloud processing. This was the computer that I was using, and there would still be times that I would let models run through the night and I would wake up and they'd still be processing. So it's important to have these powerful processors to help you get through these point clouds. For the pedestrian access ramps, it's a pretty straightforward case study, but it's important to ensure every point in the scene is captured by at least 3 different views so that you have sufficient overlap between your images. And it's important to level the laser scanner before starting your scanner. And that's just because if your scanner is unlevel, it can cause errors within your measurements whenever you're doing your post-processing. So it's important to go ahead and level your scanner at the start before starting your scanning process. And a bit of a cost-time analysis for the different equipment and softwares that we use. So photogrammetry is much more cost-effective than LiDAR, and we have it broken down here a little bit for you. So for the equipment that we're using for photogrammetry, GoPro is about $400, Fujifilm X-T30 $1,300, and the DJI Mavic 2 Pro is $1,600. The LiDAR equipment that we're using, Manley Communications has 2 Velodyne HDL32 scanners, and both of these scanners together cost $49,000. The VX15 scanner that was mounted onto that M600 drone that we use for highway asset management is $140,000. And the MapTech terrestrial LiDAR scanner that we use is an older scanner, and it's still $30,000 used. Photogrammetry requires slightly less time for in-field labor, mostly because the setup for mobile photogrammetry just means mounting the camera on the front of the vehicle and simply going out and driving. Manley Communications, when they have to set up their mobile LiDAR vehicles, they have to go through about 30 to 45 minutes of booting up all of their systems and doing calibration checks to make sure everything's running. Same goes for the pedestrian access ramps. For photogrammetry, you come to your pedestrian access ramp, you take out your camera, take your images, and go back for post-processing. For LiDAR scanners, you have to take out your scanning equipment, you have to level your scanner, ensure your scene is captured, and then you have to do the scanning. And photogrammetry requires less storage in the field. So for our asset management, all of the data that we gather using the GoPro is just stored on a small micro SD card. But for Manley Communications, their LiDAR data is stored on massive terabyte hard drives that they have to physically mail to their processing offices. So it requires slightly less storage in the field, but more storage in the office. But that can be kind of combated by the downsampling that we just talked about. So a little bit of, we'll go through a summary for you guys. LiDAR, an error of 3.48% and a CV of 0.42. And photogrammetry had an error of 4.33% and a CV of 0.41. So very close in their errors, and LiDAR had slightly more uniform distribution of points. That's what this coefficient of variation is referring to in these models, is their distribution of points. And the lower that coefficient of variation, the less variability within that model. Our UAS LiDAR was unable to accurately reconstruct sign surfaces, but it accurately mapped the surrounding terrain. On the other hand, photogrammetry could map the sign locations and show the signs, but it also accurately mapped the surrounding terrains. There was only a 0.85 difference between measured errors for both technologies for LiDAR and photogrammetry, which is pretty great considering the price difference between the two technologies. LiDAR, as I mentioned, had a slightly more uniform distribution of points. The Image-based models were much more dense before downsampling, and as you saw from the cost and time analysis, photogrammetry is much more cost-effective. A little bit of a Ped Ramp Summary. So LiDAR error 0.19 with a coefficient of variation of 0.24. Photogrammetry had an error of 0.32 and a coefficient of variation of 0.48. So it had a 0.13 difference between computed errors, which is very close, but LiDAR had less deviation in its measurements, and that's what the coefficient of variation is referring to for this case study, is the amount of variability within the error measurements. And since LiDAR's coefficient of variation is less, it had less variability. Photogrammetry took less time to gather data on each of the ramps, and it could be possible to use a drone for pedestrian access ramps and capture data regarding multiple ramps at one time, but a more in-depth analysis of that case study would be necessary to talk any more to that. And then let's talk a little bit about our pavement distress. So we had a very accurate alignment with most points having a distance of less than 0.4 from the ground truth model. So photogrammetry deviating about 0.4 from the LiDAR model. Had a maximum deviation of 3.25%, average deviation of 1 centimeter from the LiDAR model. But this was a supplementary case study, and more research would be needed for an in-depth analysis of this case study. We wanted to use the tools we had for any case studies that we had in our mind, but to talk more to a pavement distress analysis, we would need to dive more into the research of this study. And our bridge inspections. So photogrammetry couldn't capture anything regarding the underside or backside of the bridge because of the camera angle, but mobile LiDAR and terrestrial LiDAR did. The mobile LiDAR only deviated about 1.29% from terrestrial LiDAR, which is pretty impressive because terrestrial LiDAR tends to be a very accurate technology because it's stationary, you're not moving. But the mobile LiDAR was very close to what the terrestrial LiDAR models were providing. Mobile LiDAR and photogrammetry could be used for asset inventory of bridges, but not necessarily bridge inspections. Again, this was a supplementary case study, much like the pavement distress, so we would need to dive more into this case study. But right now, you could use it to inventory bridges, but as for bridge inspections, it's not quite there yet right now. So some pros and cons to the technologies that we talked about today. For photogrammetry, it's easy to use, it's cost effective, has a great accuracy for its cost with a less than 1% difference from LiDAR for both of our main case studies, provides very dense point clouds. It also provides visual colored representation of the assets because the images are ingrained in the models. As you can see down here below, you can read what is on these signs. Cons, right now it is limited by your speed of travel. You really want to be going less than 50 miles per hour. I can see that changing based on the sensors that are used. But as for the case studies we did, we were limited by 50 miles per hour. Slightly less accurate than LiDAR, and model sizes can be hard to process on some systems. As I mentioned, they're very large models, and if you don't have a powerful processor, it's going to be pretty aggravating trying to get through this processing. And let's talk about LiDAR. So LiDAR has a very high accuracy. It can gather data at higher speeds, so Manley can travel up to 65 miles per hour on the highway. The amount of data can be controlled. Kind of as I mentioned, they use smart technologies to speed up data collection as they're going faster or slow it down as they're slowing down. And another pro of LiDAR is that the point cloud is generated as the scanner is gathering points. So as the scanner is actively gathering these points, it is also generating this point cloud. But for photogrammetry, we have to take these images and then we have to input them into a software to process and create these point clouds. So for LiDAR, it's done in one step. Some cons, it's extremely expensive, as we mentioned. There's a steep learning curve with LiDAR. A lot of times there's required trainings depending on the scanner or softwares that you buy, and these trainings can be expensive. And as I mentioned, Manley Communications has to physically mail these terabyte hard drives to their processing offices, so that can be a little bit of a hitch. So to wrap everything up in our conclusion, it's imperative for transportation managers to have up-to-date knowledge regarding the current state of all of their assets, which requires a quick, efficient, and affordable data collection procedure. LiDAR is the traditional data acquisition technology. It has a very high accuracy, but it also has a very high initial cost, and it requires technical knowledge of the scanner and the scanner software in order to accurately create and extract measurements from these point clouds. For image-based reconstruction, it is emerging as a more affordable alternative to LiDAR. It has a slightly less accuracy, slightly lower accuracy than LiDAR, but for the cost difference, its accuracy is very good. It has a low upfront cost, and photogrammetry can even be done with something as simple as a smartphone or a digital camera like we use for the pedestrian access ramps. Photogrammetry performed nearly as well as LiDAR in both case studies. There was only a 0.85% difference between the technologies for asset management and a 0.13% difference for pedestrian access ramp inspections. Photogrammetry can be used as an affordable solution to lapses in model generations, and that's one of the big things that we hit on with UDOT whenever we would talk to them. So right now, Manley Communications is contracted to gather data regarding Utah's highway assets every 2 years. Now, roadways are constantly changing, so there's always going to be changing of assets and roadways within that 2-year gap. And what photogrammetry can be used for is for updating lapses in model generation. So if Manley scans 1 year and the next year there's either construction or changes to one section of a roadway, it would be easy for personnel to go out in the field with these photogrammetry methods and collect data regarding the updated section of the highway, so that whichever organization needs that information has an accurate, updated model of that section, and not, a model from a previous year. So the low cost, ease of use, and good accuracy of image-based reconstruction cameras and software makes photogrammetry a very capable technology, and it may be soon considered an acceptable alternative to LiDAR within different divisions across the United States. It comes in at a much lower cost, and though it does have a slightly lower accuracy at the time, the accuracy is very close to LiDAR, and as I mentioned, you're paying a lot less. And we'd just like to thank Mountain Plains Consortium for their support and for everybody joining this meeting today. And if there's any questions, I'd like to open the floor up, and I hope you guys enjoyed the presentation and got some important information out of it.
Thanks, Chandler. Dr. Rashidi, do you have any closing comments you'd like to make?
No, so again, I appreciate the support from Mountain Plains Consortium and also Muhammad and Chandler, our graduate student who did an excellent job on this project. And as Chandler mentioned, we are open to any questions.
Yeah, anybody, if you have any questions, please feel free to either unmute and ask your questions live, or you can simply put them in the chat and we will be sure to address that question for you. So thank you for the questions we did receive. Certainly appreciate those. If there are any additional questions, so please go ahead and put those in. Not seeing any questions come in. As I make some closing comments, please, again, if you do have questions, feel free to reach out, put that in or unmute and ask your question. Otherwise, you can certainly reach out to the research team here, and they'll be more than happy to get back to you, or you can reach out to me and I'll certainly pass it along to them as well. And I sincerely hope that you enjoyed and gained some new knowledge from today's presentation. I thought it was very good, so thank you, Chandler, for that. I encourage you guys to visit our website at translearning.org. From there, you will also be able to see the Mountain Plains Consortium website if you want to learn more about the MPC. If you want to revisit today's presentation, it will be posted on the MPC website as well as the MPC YouTube channel. And then the research papers and documentation are also out there on that website as well. If you do see a topic that is of interest to you or your peers, please do share that information so that they can be sure to attend future presentations as well. And as always, if you have any questions on TLN, feel free to reach out to us. Our TLN team will be more than happy to answer any questions and help you out along the way. With that, get out there, wash your hands, and don't forget to be awesome, guys. Have a fantastic day.